Hey everyone, let's do some more cool stuff with the dot product. So let's say you have a set of vectors, v1 to vn. We'd say that that set of vectors is orthogonal if all of the vectors are orthogonal to each other. And probably the main example to keep in mind is the standard basis vectors, e1 to en. Those are orthogonal to each other. You take the dot product of any two of them, you'll get 0. So that is an orthogonal set. Now here's another example, and it may not be so obvious at first, but the way that you check that they're orthogonal is that you actually take the dot products of all the different vectors with each other. So if you dot the first vector with the second vector, you'll see that you get 0. And then you dot the second vector with the third vector, you'll also get 0. Then you dot the first vector with the third vector, you'll also get 0. And so they're all orthogonal to each other. It's an orthogonal set. So there are a lot of cool things about orthogonal sets, but one thing is that they're always linearly independent. And this is a pretty important fact, and so I'll give you a proof. So let's assume that we have an orthogonal set of vectors. And remember, to show that they're linearly independent, we need to show that this equation, c1v1 to c1vn equals 0, only has trivial solutions where all of the c's are equal to 0. So what we'll do is we'll take that equation and we'll dot both sides with v1. And then one of the properties of the dot product is that it's linear, which means that it distributes over addition and you can pull scalars out. And so when you do that, this is what you get. And now you'll notice that except for that first term that has a v1 dot v1, every other term has v1 dotted with a different vector in the set. For example, this last term, which is actually written out, has v1 dot vn. But then that's going to be 0 because the vectors are orthogonal. And so because of that, all of the terms except for that first term are 0. And then the first term has v1 dot v1, which is the length of v1 squared. And now I realize that I should have stuck in the assumption that the vectors are non-zero somewhere, because if we know that v1 is non-zero, then we know that it has length that's non-zero. And if that length of v1 is non-zero, then the only way you can get 0 in this equation is if the c1 is 0. So that shows that c1 is 0, but then you could make a similar argument where you dot both sides by v2 and prove that c2 is 0, and so on. And so you can actually show that all of the c's are equal to 0. And so then that shows that the set of vectors is linearly independent. Okay, so let's suppose we have an orthogonal set of vectors, and then we have some other vector that we'll call b. We know that one of the problems that we solve in linear algebra is that we try to write b as a linear combination of some set of vectors. Well, as we just saw, orthogonal sets are linearly independent, and one of the things we know about linearly independent sets is that when you're solving equations like this, they will always have a unique solution if a solution exists at all. Linear independence means that there are no free variables, so the solution is unique if it exists. So how would you solve an equation like this? Well, we know that one way to do it is to make an augmented matrix, put the matrix into reduced echelon form, and blah, blah, blah. But it turns out that there's another way to do it using the dot product. It basically uses the same idea that was in the proof we just saw. You take this equation that we're trying to solve, dot both sides by v1. And then again, the dot product can distribute and you can pull out the scalars. And then again, all of the terms except for the first term go to 0. And then I could rewrite v1 dot v1 as the length of v1 squared like I did in the proof before, but I'll just leave it like this. And what we want to do here is solve for c1. And so when you do that, you get that c1 is v1 dot b divided by v1 dot v1. If this reminds you of the orthogonal projection formula, it's because it is the orthogonal projection formula, but I'll explain that a little more later. And then this was the formula for c1, but we could have dotted both sides by v2 and gotten a similar formula for c2, same thing for c3, and so on. So the general formula is that ci is vi dot b divided by vi dot vi. So this is pretty cool and pretty powerful. If you have an orthogonal set of vectors, then you don't have to go through a process of solving these equations, but there's just a formula that you can plug everything into and get the answer. So let's look at an example of this. Let's say you have these vectors, v1, v2, v3, and then a vector b that's given. You'll notice that this v1, v2, v3 are the same vectors that we looked at in the previous slide, which we saw were orthogonal to each other. So once we observe that they're orthogonal, that tells us that they're linearly independent. And then because they're three linearly independent vectors in R3, we know that they're going to be a basis for R3. And that's important because it allows us to know that a solution exists. Remember, that was one of the big caveats at the top of this slide. And then once we know that a solution exists, then we can use the formula to calculate C1, C2, and C3. So C1 is v1.b over v1.v1. And when you plug in the numbers for v1 and b, you get 15 for the dot product on top, and you get 5 for the dot product on the bottom. So C1 is 3. Similarly, C2 is v2.b over v2.v2. And when you plug in the numbers for v2 and b, you get 12 over 6, so you get 2. And then for C3, you would get 30 over 30, which is 1. And so that's the answer. The solution is that 3 times v1 plus 2 times v2 plus 1 times v3 is equal to b. So this method is really good. You probably noticed that it involved a lot fewer calculations than solving by row reduction would. But in order to use it, there are a couple of special things that need to be true. The first thing is that those vectors v1 to vn need to be orthogonal to each other. And then the second thing is that vector b on the right side of the equation needs to be in the span of v1 to vn. In other words, we need to know that a solution exists. But it can be useful to think about what goes wrong when these conditions aren't true. Well, okay, with the first condition, nothing special happens. The formulas that we derived were derived under the assumption that the vectors are orthogonal. So if the vectors aren't orthogonal, then those formulas are just invalid, and you just can't use them. But the second condition is more interesting. Obviously, we know that if a solution doesn't exist, then there's no way we can find a solution. But what goes wrong in the calculation? Let's investigate a little more. So let's suppose that b isn't in the span of v1 to vn. Then we can still use the formulas that we found to calculate ci. And we can still use those ci's as coefficients to make a linear combination of the v vectors. So actually nothing went wrong in the calculation except that we know that it can't be equal to b. Well, it turns out that this is still useful because it gives us the closest point to b in the span of v1 to vn. In other words, even if no solution exists, this formula can be used to get the best approximate solution. And actually, you've already seen the simplest version of this, which is the n equals 1 case. In that case, you have a non-zero vector v, and then the span of v will be a line through the origin. So then if you have another vector b that isn't on that line, you could ask the question of what is the closest point on that line to b? And of course the answer is going to be the orthogonal projection of b onto the line. And of course the formula for that orthogonal projection is exactly the same formula where the coefficient of v is v dot b over v dot v. So the general picture is just a higher dimensional version of this. The span of the vectors v1 to vn is going to be some kind of a subspace, and so let's just call that subspace w. And then if you have some vector b, then you can define the orthogonal projection of b onto w by this formula. And this will give us the closest point to b in w. So this is something that has a lot of uses. It can be used for geometry if you actually are trying to find the distance from, say, a point to a plane. It can be useful in physics, for example, in force problems like what I was talking about earlier. But more generally, it can be useful anytime you have a system of equations that you're trying to solve, but that system of equations doesn't have any solution. And there's a really important application of that, which is finding best fit lines in statistics. So that's something that we'll talk about later. Okay, so here's an example of a geometric problem that uses what we've learned. Let's say that we have these vectors, v1, v2, and b, and we're asked to find the distance from b to the plane spanned by v1 and v2. So the first thing you're going to want to do in a problem like this is check whether v1 and v2 are orthogonal, because they need to be orthogonal in order to use that orthogonal projection formula that we just found. And so this is straightforward to check. You just calculate the dot product and see if you get 0, and we do. Now, you're probably wondering what you would do if they weren't orthogonal. That's a really good question, and that's something that we'll deal with a little bit later. But since these vectors are orthogonal, we're good. So now what we'll do is we'll let W be the span of v1 and v2. So this is just to give a name to that plane. And then we can use the orthogonal projection formula for the projection of B onto W. And now it's really just a matter of plugging the vectors into this formula and doing all the arithmetic. So I'd recommend that you pause and do these calculations yourself. So when you calculate these dot products, what you get is v1 dot b is 35. And then v1 dot v1 is also 35. Just a coincidence, there's no reason that that should happen. And then in the second term, v2 dot b is minus 28, and v2 dot v2 is 14. So then this simplifies to v1 minus 2 times v2, and we can plug in the numbers for v1 and v2. So this is v1 minus 2 times v2, and when we simplify this, what we get is 3 minus 9 minus 1. So this is the closest point to B in W. So because this is in 3 dimensions, it would be hard to draw like a really accurate picture of this situation, but this is my attempt at a sketch of the idea. You've got your two vectors, v1 and v2. They're orthogonal to each other, and they span a plane. And then you've got this point B, which is not on the plane, but then we can use this orthogonal projection formula to find the point on the plane which is closest to B. And in this case, the point that we found is v1 minus 2 times v2. Now, we still haven't actually answered the question. The question is asking for the distance from B to the plane. And to find that distance, we want to find the length of that yellow dotted line. So in other words, the distance from B to W is the length of B minus the orthogonal projection. So we can put in the numbers there, and then we can actually do the subtraction. And we get 206. So this is actually the vector that represents that yellow dotted line. And then the length of that would be the square root of 2 squared plus 0 squared plus 6 squared. And that is the square root of 40. And that is the answer to the question. Okay, so there's one more quick thing I wanted to mention, and it's mostly just terminology. So the first thing is that if you have a vector whose length is 1, then you call that a unit vector. So here are a few examples of unit vectors. You can just calculate their lengths and you can see that you do get 1. And it is worth emphasizing that the standard basis vectors, e1, e2, e3, etc., are unit vectors. And then the next thing is if you have a set of vectors that are all unit vectors and also orthogonal to each other, then they're called orthonormal. So orthonormal includes both being orthogonal and being unit vectors. And the reason why this can be useful is that the formula for orthogonal projection becomes a little bit nicer when you have orthonormal vectors. And the reason for that is that when you have a vector that's length 1, that means that its dot product with itself is 1. And this is simply because the length of u is the square root of u dot u. So the only way you can get a length of 1 is if u dot u is 1. And so what this means is that all of the denominators in that orthogonal projection formula will be equal to 1, and so you don't have to worry about them. And so in the case where you have an orthonormal set of vectors, the projection formula doesn't have those denominators, and it just looks like this. So you'll see this formula a lot because it does make the calculations nicer, at least when you're doing abstract calculations. You can sort of assume without loss of generality that all of your vectors are sort of scaled properly so that they're unit vectors, and then you can use this formula, and it makes the calculations nicer. But in practice, unit vectors themselves are kind of ugly, except in some very special cases. And so you see this in the examples that I gave you. You have like square root of 2, square root of 3, and typically this is what unit vectors look like. So the trade-off is that you have nicer looking abstract formulas, but uglier looking concrete formulas when you actually plug in the numbers. So the ideal thing is to be aware of both versions of the formula and to use the one that's most convenient for any given situation that you're in.